it happens to be that you guys are in a unique position because between the University of Nebraska and the University of Iowa, we pretty much have the most extensive collection of astronomy demonstrations between us. And so when we meld them together, you have everything you ever need for a course, okay? And so that's kind of the way we have lined things up. We have pretty much gone through and picked out 40 demonstrations that you would probably use for a general astronomy course, okay? And we have arranged them so that we're going to go through them in your book in about the order that you would use them in a general astronomy course. Give you a little background on what you have in the book there. The first thing you have is a little explanation is what I'm going to give you here. And this goes before the contact information that's in your book. But the explanation is that all of these demonstrations that we have a number on them. And the numbering system came from an organization that Cliff and I belong to, which is called PIRA, which is the Physics Instructional Resource Association. And what we have done is we have taken a collection of the most popular and extensive references on demonstrations, and we have filtered all of those. And Cliff, if you want to hold up one of those purple things, what we have done is made that into a bibliography, okay? And so if you're talking about a demonstration, especially if you want to contact us later on about something that we have seen here and you've not written down correctly in your notes or written down carefully enough so that 2 years down the road you can't remember what we were talking about, you call us up and say on 8/8/2030 I had this question, and we'll know what demonstration you're talking about, and then you ask the question and we'll be okay. But anyway, the Physics Instructional Resource Association has gone to great lengths to create a master list bibliography, and that's what we have here. Now this is the hard copy, and Cliff, I'll let you pass that around so that I have 3 hard copies here that you can pass around and kind of take a look at. You are not really interested in having a hard copy, and I'm not going to spend 20 bucks giving each one of you a hard copy, okay? What you're more interested in is this bibliography is online, and it has a searchable index so that you can just put in something like black holes and all the references to black holes, and the numbers all come up, okay? So that's basically PIRA's claim to fame. Is one of the things that we do is kind of organize everything so that we have a definite numbering system and how we want to use that. Okay, so the first thing you're going to find in the page of your notebook is the contact information from myself and Cliff. Like I said, 2 years down the road, it gets pretty hard to remember what you were thinking when you made some of the notes in your notebook here. And so feel free to contact us. And there are a couple ways to do it. You can use the contact information in there, and you can use another thing that I'm going to talk about in a little bit. But the other thing is how to use the bibliography. Like I said, you want to do the search thing, okay? You don't want to necessarily, unless you're organizing demonstrations for your school or something like that, you don't want to spend a lot of time learning the numbering system and all that. So you want to do a search. Anyway, here's what we have done. We do something called the demonstration classification scheme. We've gone through, and basically this is the website that you want to look at right here, the Physics Learning PIRA thing. So if you go there, you'll find the searchable index, and everything you need is there. But basically, just to give you a small demonstration of how this is laid out. If you look at it, you're going to come, if you search for a certain demonstration like the monkey and hunter, you're going to come up with a bunch of examples. This one says Fryer and Anderson MB16. If you look in a Fryer and Anderson book, you're going to see the monkey and hunter demonstration described, okay? We give it the number 1D6030. 1 is mechanics, 2 is fluids, 3 is acoustics or oscillations, 4 is thermodynamics, 5 is electricity and magnetism, 6 is optics, 7 is modern physics, 8 is astronomy. So all the numbers that you should see should have 8 something today. But basically that's how that's laid out, and then we have gone through and given them the 60.30 gives you about where in the course and under what heading and stuff like that. And then we just have a short explanation of what goes on there. Okay, so that's pretty much how the bib works, and that's how the numbering system that you're going to see today works. And here's just a list of some of the references that we've gone through and cataloged into that bibliography. Okay, we've got Fryer and Anderson, Sutton, which is a real big one, Hilton, Miners. The more recent ones are Dick and Ray, and we have one by Clint Sprott from the University of Wisconsin is also on there now. TAPL, if you really want to get a hold of Cliff and I, we have our listserv for the physics demonstration people, lab coordinators and stuff that do a lot of this kind of thing. And TAPL is our listserv, okay? The instructions on how to get on TAPL are in there. It's real easy. If you can't get on by doing it yourself, just contact the list administrator and he'll put you on. But basically what we do is have a lot of people who just lurk and read the emails that most of the big wigs like me and Cliff send back and forth and learn about things, and if you have a question then you can ask on TAPL, and that's how we usually get things done. For us on TAPL, if it takes more than 30 minutes for us to ask a question and get a reply, we're having a real slow day, okay? So most things you can get 6 or 8 different answers from people if we have a question within 30 minutes. So there are a lot of people out there who really maintain and make that work. Other email lists that you guys might be interested in are the Forum for Physics Teachers, Physel. That's more like for the college guys, because there's a lot of real theory and real hashing that goes on between the college professors about questions that are asked there. For the high school people, probably PhysShare is more applicable, because that's where the sharing resources and stuff go on. If you are looking for people who have already made the wheel and not wanting to reinvent it, then you go there and find your resource materials. Okay? Other online resources. So in the back of your, I can't remember how I ordered this. Let me look here. I ordered this so that TAPL was the last thing. Okay, so if you go back to the back after the demo page, you'll find that there's also another section that says Physics Demonstration Resources Online. So these are demonstration sites across the country that you can look at for particular demonstrations in astronomy and stuff. Like I said, I've done most of that, and most of these guys only have like 6 or 8 demonstrations and don't have 100 like I and Cliff have. So a lot of that goes on. And then there's other physics demo sites. Bill Beatty, a guy out in Washington State, I think, has a lot of things on Tesla coils, plasma tubes, induction, and he does a lot of gonzo type work. So, you know, throwing light bulbs into microwaves to see what happened and that kind of thing. That's what he does. The Wonders of Physics page with Clint Sprott, and then American Association of Physics Teachers has a whole site that they do nothing but collect links to different resources that you can have. All right? What else have I forgotten to talk about? Clicker questions. So Cliff came up with an idea. So the last half of your notebook is nothing more than questions. If you are fortunate enough or want to have some kind of polling type thing, a lot of them have the little clickers that you can poll anonymously in class, if you've seen those. But a lot of people just want to ask a question and have people raise their hand as to what the right answer is. But basically it gives you a little guide as to, are the students really understanding what you're saying during class? And before you get to a test and discover that, you know, half of your class didn't understand certain concepts or anything like that, you can go through some of these questions and actually be able to figure that out. There are a whole, I think there's 112, 113. I think there's 113 because Cliff has 2 17s or something in there. So, I did discover that.
Those are great for peer instruction too, to have kids talk about the questions before they answer with their clickers.
And so then the last thing is that I have also compiled, right after TAPL and right before all the demonstrations in your notebook, there are a list of other PIRA numbers there of demonstrations that are useful for astronomy, but because their main usage is in things like mechanics or heat and fluids or something like that, they have a different number than 8A something. So I have compiled a list of those for you to play with, okay? So just using this book, you should have a lot of resources available to you for astronomy applications or teaching that can help fill out maybe your curriculum if you are ever asked to teach an astronomy course. Anybody here regular astronomers besides this guy? The rest of you, I take it, are just teachers who were in something else and were asked to teach astronomy. That's usually what happens in Iowa, is that, you know, you're a biology teacher and, oh, we don't have anybody to teach astronomy, we'll let you do that. And so that's usually how that comes about. So I find that usually about half my audience is not professional astronomers, all right? So it works out pretty well. The PIRA 200, if you look on our PIRA main website there, you'll find something called the PIRA 200, which is basically the 200 most common demonstrations to use for like a general physics course. Some of those for astronomy are in here. But those have some video links and stuff. But basically this is the model that we're going to work on today, which is, you know, if we can't fix the problem, we'll find out who to blame, and we're gonna pick Tyler for that today. So everything that goes wrong that we see today is actually going to be his fault. Okay, how do I get out of this, Cliff? I lost something. You want to plug it?
No.
Just want to stand by for me. Oh, we're good. I just haven't looked behind me, that's all. There we are. Can't see my full screen mode, but we're okay. So, here's where we start, the good stuff. For orreries and celestial spheres, if you look in a manufacturer's catalog like Sargent Welch or Senko or Arbor Scientific, Pasco, any of those, you go to their astronomy section, there are about maybe a half a dozen real astronomy demonstrations that you can buy. The rest of them you have to make or come from the physics sector or something like that. The orrery and the celestial sphere are about the only two that anybody really has if they're teaching astronomy and they have bought themselves. Otherwise they make stuff, okay? And that's pretty much the whole thing around here, but we'll show you some toys and stuff that will make do with what you have. But for the orrery, Cliff, if you want to hold that, because you're going to talk about that.
That makes me hold the world.
The orrery, of course, you can buy the one in the catalog that looks like the one at the top there, okay? And it has the planets in order until Uranus and Neptune switch orders. Then it's not right, but the catalog still says that they're in the other order. But they might even still have Pluto on them. I think they still do. But the problem with these is usually they're battery run, they're toys, so they usually don't run very long, they don't last very long. The scale is not right, and there's a lot of other things. But basically, if you're trying to get your students to name the planets from the sun outward, they're probably pretty good. But for anything else, it's questionable as to what educational value they are. We actually made our own at the University of Iowa, and we only use, if you want to hit that switch back there for me, Cliff, the lights. Right, this one. Okay. So we always talk about Earth, Moon, Sun system. For most of our stuff, we don't worry about the outer planets unless we're talking scale models or something like that. And so we have the sun here, we have the Earth, we have the proper tilt for the Earth, we have the moon, and the moon actually goes around the proper number of times, but it doesn't have the 5 to 7 degree tilt off the equator, so this is always going around the equator. But the nice thing about this is that you can also show how eclipses happen. And so we line it up here. We have an eclipse right now that's about the equator, but if I take this at about 90 degrees, now you can see that my plane is up above the North Pole. So you can do eclipses because of the way this goes. And my little red pin here can be used either for Iowa City or Lincoln, because we're both about the same latitude. So I just, move it over just a couple hundred miles and we're okay. So, so all that works out. But basically, you can see that this is nothing more than some gears we had sitting in a box and some light bulbs and put it together. And that's usually the most effective orreries that I have seen are usually some that have been put together like that. So nothing too expensive or extravagant that you need to do. Okay, so Cliff, if you want to unplug me, and then you go ahead with that one.
The celestial sphere.
Yep.
This is a celestial sphere, and actually you could think of it as kind of a little analog computer. It has everything on it you need to know to figure out things like rising and setting positions for stars, as well as where the sun is at a particular time of day. I have it set up right now for Lincoln, Nebraska, and I have it set up for sunset, so let me turn the world around here a little bit and see if we can bring us some daylight. There we go. That would be about noon. The circle on the inside here is called a horizon circle, and it represents the horizon, so you can look on it to find out, say, in what direction the star Menkar is rising or setting, and also you can use it to find the altitude, the azimuth of other objects at various times of day. You can use it to figure out where the sun is in the ecliptic, what constellation it is. Right now we're just going through the constellation Virgo for you astrology fans. I'm sure there aren't very many of those in the audience. But anyway, it's a nice thing to show. If you have a TV camera, you can get up close with it and point out the individual items on it. These days, there's so many nice planetarium programs that some of these sorts of things are kind of passe, and you can just go to a planetarium program to deal with those issues of settings and risings and so on. And you can figure out the hour angles of stars and so on, and again, where to expect to be able to point your telescope, whether you've mistakenly assigned an observing time that makes you point your telescope rather down into the ground, which is a bad thing, or if it's going to be nice and high in the sky where you can see it. Okay.
Next thing we're going to do, by the way, those books are yours to keep, those notebooks, so make sure you make your notes right on the same page as the items that we're talking about. So don't worry about messing them up. That's your prerogative there. Also, we're real informal here, so if you can't see, stand up or move over. We're going to be using like both sides of this, and I know that there's going to be issues with you guys over there. When we're talking planets, the first thing we usually talk about, which is why we need the tops in the gyroscope here, we talk about precession and nutation. Mostly we talk about precession, which is basically real easy to show if you have a top like this, because you can move the thing so that it has a real big precession ring. Okay? If you have something more like this, that's still okay. Where you have the gyroscopic type top, and Cliff has in his hand here a little mask that he can put either there or in the back, and when you do that, you can see not only the precession, but now he didn't do it real gently, so he has a pretty good nutation going there also. But you can also show the nutation with the top, because these things aren't that well balanced, so they always have a little rotation motion going with those also. Okay, so fairly common to do, and if he can get that one to go, he did it once already this morning. I think he's used up his quota, so.
He thinks I'm pressing my luck.
I'll get that out of the way for you.
These are, if you're old like me, you maybe, actually, this is a toy that my father used when he was a boy, not this particular one, but it's the same kind of top that they prized and enjoyed. And all you do is you give it a little toss on the floor there, and
get it to dancing around on its tip, and it'll spin and spin and spin and spin. I discovered to my chagrin that this is a skill that children no longer have, because I used to provide them for a little science sessions with grade school kids, and I found that I needed to train them how to throw tops. And in order to do that, I had to train graduate students how to throw tops, and they started complaining because it was physics graduate students, so I said it was too hard for physics graduate students. Anyway, I have lots of tops. If you want one, I can probably give you one.
Okay, so now, Cliff, we need our sun. Alrighty, our big sun. So for phases of the moon, there are a couple ways to do this. I have mine, and you can see the thing that I have up here is I have a wireless camera mounted here, one of these cheap $40 wireless cameras you can buy from a lot of places nowadays. Just have a moon globe here that we can change around. And you know, usually I try to make sure that it's lined up so that the right side of the moon is facing the right direction. Anyway, this is our view from Earth right here. And what we can do then is we can show things like the lunar terminator line. So this would be you know, no moon to full moon, and then back again. And I can never remember which way the rotation rate is supposed to go, so I might have the terminator going the wrong direction. But anyway, this works out pretty well. But obviously you don't need something this sophisticated for a lot of you. You would use something more like this system here, where you would just have the Earth and a moon. These are about the right scale, actually, and so you would be able to move these around, and wherever you're sitting back over here, if you're sitting over here, you're probably going to see a no moon right now, whereas you guys over there might be seeing a full moon. So you'll be able to see, the audience will be able to see what's going on with this type of a system. But it gets the idea across as to how the lunar phases happen in relation to how the Earth-Moon system is working there. Okay? I think that's good there. We're going a little fast here because for you guys who haven't never been to a pyro workshop before, we usually do like 50 demonstrations in a half a day, 100 in a day. We got 40 here to do in an hour and a half, so 3 minutes apiece is all we're going to give you. But if you do have questions, please shout them out so that we can answer them right away, or we can have you come back and talk to us later. Okay, so the ellipse drawers, Cliff has his and I have mine here. Usually all these are some system of either magnetic or suction cups or something like that. Just basically your two foci and some way to be able to draw the ellipse as you bring the strings around and keep them tight. I'm not very good today, so
Either mine got looped around on my own.
yeah, I did mine too. So anyway, you can get the idea, and then you can move the focal points closer or farther apart, depending upon how you do it, and get your ellipses and draw them one on top of the other, and show what happens as you increase that.
There we go.
But usually it's not too complicated of a system to make some kind of a way to make an ellipse. For us, I'm better if I do it down this way, but you know, for a teacher, you have to learn how to use the chalkboard. So there you are. Cliff, you want to hit the next one there? Does anybody have any questions so far on anything we've gone through? All right. Retrograde motion. All right. A lot of places don't have a way to show retrograde motion other than in astronomy programs such as Starry Night or something like that. At Iowa, we're fortunate enough that one of my predecessors went and made one of these. It's not too difficult. Basically, all it is a clock mechanism, except for the hour hand moves faster than the minute hand. So Now in our system, this is the Sun, the Earth, and Mars out here, okay? And we have added this so that you can see when the two planets go in retrograde, because you'll see this arrow will continue this way and then it will stop and back up a little bit and then it will come around again. So if we raise this up so you guys can see it fairly well. I just need to make sure my cord's out of the way when this works, okay? So basically you can see, all I have a little motor running things. You can see when it's going this way, and then when it backs up, this arrow goes back, it comes back, so you can see when the two are in retrograde. And basically this is my physical model of what you'll see on the planetarium programs, okay? And you know, as an extra kicker, we have it so we can take it into prograde if you want to. But nobody talks about that anymore, hardly. We used to do it all the time, but now we're all retrograding, so. But a lot of places don't have any kind of physical model like that. They're fairly simple to make, even, you can make them even simpler, because I've seen people who have just done it with, by moving the hands or with a hand crank. So there are several different ways to do it, but again, all of this is your ingenuity, and make it yourself, because you won't find this anywhere that you can buy. Scale models of the solar system. We have several here. It depends on how extensive you want to get. For me, usually, my professors or teachers don't want to get too extensive. So the two simple models I have are, if this is the Earth, this is the Moon, how far apart should they be? This is an inch, and this is a quarter of an inch, I think. They should be like 30 inches, which should be about here. That's in scale, okay? If this is an inch. Another scale is for the Earth-Sun system. If you have one of these BBs here and a 12-inch sun, these would be 100 feet apart, so like twice the distance from the front to the back of this classroom would be the scale for this, okay? Or, and this is the one that we hardly ever use, but I still have it, a scale of the size of the planets. And you can do distance here if you want to, because you'll find in your notes there, the first one is like the 1,000-foot, maybe it's the last one, the 1,000-foot model of the, so basically the sun would be out over there and 1,000 feet away is Pluto somewhere, and then all the rest of them are scattered in between. But basically what you can do is, if you look online, there's one that should say relative size of the planets or something like that. So here's our Mercury, okay, which is, I think, 3/8 of an inch or something like that. So we have the Earth, or Venus, and we have the Earth with its moon, okay? We have Mars in scale, Jupiter, Saturn without the rings, because, you know, I'm just too cheap to make them, and they take up too much room for me. Neptune and Uranus here, and then for those of you who still talk about this minor planet, Pluto is out here, this little BB at the end, okay? And I actually doubled the recipe of what you'll find online, because they were using like 0.5 millimeter size beads or something like that for Pluto, and so I doubled that so I could actually hold it in my hand. But basically something like that is really as extensive as most people get on doing scale model of the solar system or scale model work. I should say that on this system here, the sun would be 109 inches in the diameters, which means that it's like, what did I say, 9 feet 1.2 inches, which is like from here to that wall is the diameter of the sun on this scale right here. So if you can find a beach ball that big or a weather balloon and bring that into class, then you would be able to show the sun also, but I don't get that extensive about it, okay? So simple on the scale models. I've given you some web pages that you can look at to find stuff, information on, and so unless there are questions, we will go on. All right. Feather and penny is where we're at right now. So the feather and penny, obviously that's the standard classic that everybody uses when they're talking about free fall, or how objects behave in a vacuum. And Cliff, you had some other comments that I remember.
Yeah, well, first of all, we use actually, in this particular apparatus, a ball and a feather. The ball is a so-called unhappy ball, and I use it because it doesn't bounce. And the feather is a donation from my personal pet parrot, Thela, who was kind enough to donate a feather for the cause. Anyway, of course, if you drop them at the same time in the air, the ball reaches the floor much faster than the feather. If you, on the other hand, have a nice big vacuum system with a feather and ball up there, and you remove almost all the gas from inside the tube. This is a pretty fast pump. It still takes a while because it's a pretty big tube. You of course find something different. This was okay, let me just turn that off so that you don't have to hear me over the noise. Anyway, I'm going to release the current. I'm going to stop the current with an electromagnet up there. It's going to release a little shell, and the ball that I have on my right side and the feather on the left side are going to fall at the same time. And notice how long it takes them to, whether they hit the bottom at the same time or not. I'll do it on the, I'll do a little countdown. 3, 2, 1, 0. And down they go and they hit at the same time. I like to tell students that this isn't just about what happens here on Earth, but this little experiment has implications for how the universe at large works, because it gives a very strong indication that there's a relationship between the geometry of space and how things move. Otherwise, you wouldn't expect things with different masses to behave this way under a particular force. It's kind of a huge coincidence that everything should follow at the same acceleration.
Okay, questions on that? Obviously, a lot of us don't have that elaborate of a system, so we just use the glass tube that we can switch back and forth like that. We still use that at Iowa. Okay, we're going to let the expert do the inertia demo. So that if he breaks it, it's not.
I like to tell people this is an old magician's trick, and I just wish I had an old magician to do it. But here we go. The idea is you have a nice slickery tablecloth with a plate and some silverware on it, and you give it a snap, and the silverware and the plate more or less stay put. And the explanation is that these objects have inertia, and it requires a force to change their state of motion. There is indeed a force between the cloth and the plate and the fork and knife, but that force, because this thing is jerked out so quickly, doesn't act for very long, and it doesn't give the plate, fork, and knife much time to accelerate. Consequently, they more or less stay put while the tablecloth is long gone, and there you have it. They stay on the table because of their inertia.
Now, there are other ways to do that. One other way that we find that is fairly popular is to just take a 1 kilogram mass, put a string on it that's not very hefty, and if you pull up very sharply, you can break the string. If you pull up real gently, you can lift the kilogram mass off the floor. So there are a lot of different ways to do some of these things, so don't think that what we're preaching up here is gospel that you have to use, okay? You can use your own imaginations for some of these. Okay, persistence of motion, that's Cliff's baby up here.
This gadget here is an air track. I'm sure most of you have seen these things, and the idea is that there are lots of little holes in the top of it from which air is blown through, and it causes a little glider on top of it to float on a cushion of air, and consequently when it moves with very little friction. And it'll just keep going back and forth in a most boring fashion at a constant speed, more or less. It loses a little upon bouncing at the end of the track, and in a straight line. And what we like to tell students is that this is the way most things move in the universe. In the freedom of outer space, where there isn't anything to oppose their motion, they move very nearly in straight lines at constant speeds. Even the Earth or the Moon, if you think about it, if you measured them over just a short interval of their orbit, it would be hard to tell that they weren't moving in a straight line. And of course, if you get more technical about it and start talking about general relativity, we actually say, well, in a sense, it is a straight line, and we'll talk a little bit more about that later. Okay? All right.
So then once we talk about constant velocity or persistence of motion, however you want to do it, you're fine. What we usually do then is we have to go and talk about acceleration. And so we have a little cart here that's fairly nice where we can punch the button. And we'll apply acceleration for a certain amount of time, and then we're in constant velocity after that acceleration has been done. I'll do it one more time for you guys over there that didn't see that want to stand up. But basically what we have is just a little fan cart here that we can turn on for like a second or 2 seconds or 3 seconds, whatever interval we want. And it gives us enough time to get away from the fan blade before it does. Right? And so I have it accelerating for half of the track here, and then for the other half it's just in constant velocity. So you can kind of get those terms across astronomy-wise with an apparatus like this. And obviously you don't need this. You can have a little spring that accelerates it and then moves it out, or some other type of impulse device to get that up and running.
Is that a switch that you make? Is that a special switch that you make for that?
No, actually that's an apparatus you can buy from Pasco.
I bought that, but
Yeah, you buy the little switch box separately.
Yeah.
And
The
it's a
little
real
switch
handy
box.
thing because it gives you several choices about how long to leave the motor on.
Hot switch up here, and I think this just pulls apart, and this comes off of the top here. So it's just another accessory, but you can make your own. I mean,
Yeah, I use that a lot, and as Dale says, it's good because it keeps your fingers out of the fan. There's nothing worse than having your fingers caught in a fan blade in front of an audience. It's just so good.
It works well, and you know, if you have the money to spend, Pasco is a pretty good place to spend it, but they're a little pricey sometimes on some of their stuff. And a lot of this stuff you can make yourself if you have a little ingenuity and know anything about electronic circuits. So it's kind of a unique thing, but it works very nice in the astronomy setting if you're talking astronomically. Okay, ball on a string. Several ways to do this, but usually you're talking circular motion or orbits. And so obviously what you want to do is have a ball on a string, and I use a tennis ball. And notice that I'm not swinging this toward you, so that when I let it go and it goes in a straight line, or it's supposed to, it's not going to hit somebody back there unless they're asleep already. And then you let it go. But basically, if I let it go, and it should go, you know, fairly straight, you're going to find that if you set it up this way, it's going to have a little arc to it. But for half of that, it should be fairly straight, depending on how much velocity you put on this thing, of course. But in our lecture rooms, we have teachers who really swing that. I have one who actually puts a string on here that breaks when he gets up to a certain velocity, so it takes off. And so Cliff has a different way of doing it, though.
I have a little metronome here, and what I do is this. I set the metronome so I can swing the beanbag so that on every click, it's right in front of me. And then I ask the person sitting right in front of me, if I let it go on the click, is he going to get hit on the nose?
Hopefully not.
Hopefully not. And some people get real worried about this, but here I go.
Depending on your
2,
rhythm.
3, 4, 5, 6, and off it goes that way.
Of course, we can always, you know, we can really make him work hard if we wanted to play with that. So. But there's a lot of ways to do that, and like I said, a lot of that is just the flavor of how you want to do your presentations or set up your lectures. So not to worry about, you know, the things that we've shown you have to be done that way. You add your own little touches and flares because that's what teaching is all about. So the next part that we have is some spring apart cars. Basically what we have here, you can do this on the air track, but a lot of people don't have the money for an air track, so the Pasco system works all right, where you have fairly frictionless cars that have really nice bearings on the wheels and stuff. And so you can do things like put them, shouldn't do anything, but usually have a little bit, because the wheels usually have a flat spot. And I don't have my little flippers. There's a little, oh, what's this is for?
That's what that's.
See, I just didn't know. I use a ruler, so. But basically, it'll have a loaded spring here, and if I flip them, since this cart weighs a third as much as that cart, because each one of those bars weighs what the cart weighs. So you could actually set these at 1/3, 2/3, and watch them hit the ends at the same time and do a lot of things. Yes, sir?
Do you have an easy way to add weights to the air track gliders?
I do. My air track is a little bit different, but for these, the only way to add weights is to cut the cars that I know of, because we have cars that are half that size, a third that size, and then the mass is proportional. But there's no easy way unless you have lead weights or something.
I try to balance weights on the top, but they tend to fall off.
Well, the other thing is you can only add so much before you start pinning this thing down to the air track, because the blower only holds up a couple 100 grams nicely.
There's one model that have pins on the side that are out, and you can put circular weights on it easily.
But you got to balance it, you know.
When they bounce, when I just set the weights on top, if they
then
bounce,
inertia takes it off. Well, that's another inertia demonstration. We do it by putting Homer Simpson on here, you know, and letting him go without a seat belt. But yeah, there's a lot of ways to do that. But for these, I haven't found a real convenient way to do it. And nowadays you don't want to add lead weights, so you got to buy the expensive brass ones, and that takes more money, and a lot of people don't deal with that very well. So there's a lot of other things that you can do. Yes, sir.
Because I'm an old guy, but I got the old PSSC collision carts, you know, with a little spring. And they're just 2x4s.
Yep.
With the spring on them, and you can add weight to them. And
you can
take
still
it
buy
down.
those if you want to. Senko
Right.
has them again in their catalog. So there's a lot of different spring cars. You don't have to have the rail system that Pasco sells, but they do have a nice system if you are able to afford it. But there are separate systems that you can buy that just show the collisions, or a cart that rolls across the floor, anything like that. Okay, so now we're down to the dangerous part of the demonstration, and that's throwing the dumbbell. And Cliff and I weren't sure how we were going to do this, because we didn't have very much room after we got everything else set up. So anyway, the whole thing is, when you're talking binary stars or Earth-Moon systems or anything like that, you're always eventually end up talking about a center of mass somewhere of the 2 or 3 body system. So for binary stars, you'd have a center of mass here. We just have 2 soccer balls that have different masses, and have them on a PVC pipe. And if I can, is this the way to do it?
That'll work.
If I'm able to throw them, I'll let you do it. Here we go.
The idea is to sort of give it a little twist and not try not to hit anybody. You're a brave man. But here we go. Okay. If you let your eye follow the dark spot where the center of mass was, you can see that.
Should have been about that position. So I use one that's a little smaller, but for this one, you know, he would throw it up in the air and loop it around this way if we didn't have so much stuff up here in the front. But you get the idea. There's a system that you can make to show Earth, Moon, binary star systems, what is it? White dwarf and a red giant. You know how they rotate around each other. And so there's a lot of useful discussion that can take place about this type of system.
You can do them on a string too.
You can do them on a string. They don't have to be rigid. And there's a little bit more challenging to get those to work right. But I've never been able to throw a bolo, so doesn't work that well for me. Okay, so we have next is the squeezatron. For anybody who's used anything or seen anything like this, this is the thing that is dangerous because it'll come around and whap you if you get too close to it. But basically what we have is masses here that would move in and out. And so once we get this rotating, if we pull on this, we can change the center of mass. So this is basically your ice skater type thing. If you have a rotating stool and a couple of masses that you can move in and out, that's what this is, okay? This is just a model that's tabletop, so we don't have to have students up here getting dizzy, or more likely professors getting dizzy up here and then falling over in front of their students. But basically this is a simple model of what's happening, and rotational inertia, I can't remember what I call it now. Anyway. Conservation of angular momentum, duh. You know, you gotta excuse me, I'm a chemist doing this stuff, so, you know, once in a while it just completely escapes me as to what we're doing. Okay, Cliff, can we, yes, we can darken this, right? You're good. So eventually, at some point in time, you guys will want to talk about electromagnetic spectrum. In our case, we use a variety of things, but a lot of people will have nothing more than an overhead like this that came with their textbook materials, or they will use something from online to show them. And I think I have a couple of addresses online where you can get the electromagnetic spectrum online as well. But we also have a couple of things here that are unique to maybe some of your experience. If you don't watch Ghost Hunters a lot, then you'll like this. So this one needs to be plugged in. Because what I have here is a infrared camera. And so when you're talking about different parts of the spectrum, you might want to bring in a radio. You might want to bring in some gamma sources from a radioactive source, or some other X-ray tubes, if you have any. Microwave oven, maybe. Roast some marshmallows, see what happens. But for our purposes, we're going to look at the audience. This is what you guys look like in the IR, okay? And so it's fairly unique, gets you thinking a little bit. The other nice thing about this is I can take a blue balloon and blow it up and hold it in front of my face. You can't see through it to see my face. If I hold it in front of this camera, you'll be able to see through this and still see the audience. So.
Shine out on the face, just the eyes.
On my face? Cliff works really well. Cliff, if you want to stand over here. Because the unique thing about Cliff that I found is we want your glasses on, man.
Glasses on, okay.
See, the unique thing about the glasses is they're much colder than the body. And so they show up really, really well.
It's yellow, red is hot.
Red is hot, blue is cold.
And yellow is medium.
I just have it on an automatic scale, so when I scale something, it automatically finds the correct wave temperature region to put it in, and that's why it stops once in a while when I'm panning the audience.
You can do things like show your hands and then rub your hands together real fast.
Yeah, and you know, or drop a lead ball on the table and then look at the spot where the ball was, and you'll still see the thermal radiation off of that. So there's a lot of things, but basically, when we're talking astronomy, what we're talking about is different regions of the electromagnetic spectrum. And if you have that available, you're fine. You know, the FLIR cameras, I used to think that those were real real hard to find, but it turns out that, you know, most of your university or college power people already have one that you can borrow, or your local power plant has one because they take it around and do surveys of customers' homes with that, so you can get that guy to come in and play with you for a session.
With the same cost.
I know what that one cost. This one cost me $6,000, which is why most people won't have one other than a large university. But like I said, there are a lot of places out there who do have them, especially power companies, and they're more than willing to do outreach a lot of times. So they'll come out and talk to your class, or just show it in your class as part of their customer outreach thing that they have to do to keep their government licenses most of the time. So a lot of those guys have, you know, don't think that they don't want to be bothered, because a lot of times they have to be bothered to keep their federal contracts going. So
you can just use a regular video camera, especially the ones with
you
night
can
vision and see remote
use a
control.
black and white one though. Well, it depends. A regular video camera will do that if you have it on night shot or something like that. But what it usually does is it goes to a black and white part of the spectrum. So if you just have an old black and white camera, you'll be able to see into the near infrared. And so things like your remote control will blink real brightly, a lot of other things, but this one goes into the far infrared, so everything looks a whole spectrum different than what you're used to seeing. Okay? All right, so we are on to, I got it. So our next one, I think, in your book, and we're going to combine two. We're going to talk about the projected spectrum with a grating and a projected spectrum with a prism at the same time, because they're the same apparatus, you just use one different from the other. And so Cliff, if you want to go with yours there.
Alrighty, this is just a,
I got the lights.
okay. This is just a projector that I put a slit in where the slides ordinarily go, and what I'm going to do is move a prism in front of it, and when I do, you see a very lovely spectrum over there. If I get the angle just right, you get the best dispersion. And if we, one of the things you should notice about this is that the pictures in textbooks don't do it justice, nor does a TV camera do it justice. The colors are just gorgeous, and I always like to tell people that's why it's important to see the real thing, because you really do lose a lot in translation sometimes. The other spectrum we have for you here is, let me turn this off, is from a, well, I was going to show the mercury spectrum. This guy is a mercury arc light, and in front of him, where you can't really see it very well from the audience, is a combination lens and grating, and I have projected on the wall here then the spectrum from the mercury light. You can see a very pretty blue-violet line, a green line, and actually, if you look up closely, this brownish sort of line, yellowish brownish sort of line, is a doublet. There are actually two lines there, and they're very close together. And somewhere here, I left a
Screen, I saw it. Where did I put it?
Oh, there it is. There are two over on the left there.
Actually,
yeah.
there's three.
If you take a fluorescent screen, you can see some lines that you can't see with the naked eye. These are in the ultraviolet and far ultraviolet, which is why you don't want to stare directly at a mercury lamp for too long or expose your skin to it too much, because these are the photons at these wavelengths are quite energetic and can do damage to your skin or to your eyes. So anyway, and if, well, I should hold this up upside down, and you can see the reflection off the white part of it, but you don't see the ultraviolet lines until you get to the fluorescent pink part of it.
Okay. Okay. The other thing, he was doing this with a grating, and this one, the rainbow spectrum there with the prism. When you're talking rainbow, whether you're talking the rainbow with a prism or with a grating, the one thing you should realize, all of you should already realize, that the spectrum is reversed with the grating, so that the red is on the left, whereas the red is on the right over here. And so That makes a difference sometimes to some students because they'll see it in the book and then they'll ask you, why is this spectrum reversed? It's just a function of whether you're using the prism or the grating to do that. But you can see also that with the grating, we usually get a much greater dispersion than we get with the rainbow spectrum. Although the rainbow spectrum looks much more nice and intense, a lot of times you want to have it spread out so that you can talk about just portions of the visible spectrum instead of trying to find a small region in the prism part. Okay? Yes?
Thermal camera at the spectrum.
Oh, that's, I've never done it before, so I don't know.
I mean, directly at the light, not into the bright light.
You mean into this light or?
Yeah, under the spectrum, pointing so the spectrum is going into.
Oh, I see what you mean. What? There you go. All I'm seeing is the all I'm seeing is the background people there.
Why don't I put my board? Almost as false colors on the infrared.
Yeah.
You're not seeing much temperature gradient.
No, they're going to say the temperature grading is probably less than what my camera is able to pick up. You know, for $12,000 or for $25,000, I could have got
A little bit will show you for real spectrometer,
Yeah.
will.
But I wasn't willing to spend that much, and so, you know. All right, so the next one we have, Cliff, is melt the nail.
Oh, sure.
And essentially what we're doing with this is trying to show some forms, well, Kevin Lee is the expert on this. What are we showing with melt the nail, Kevin?
Beads locked largely.
There you go.
Let me turn these other guys off right fast so that this will show up in all its
I've heard
glory.
that the students just love this one. I think it's this possibility someone's going to get zapped.
Anyway, what you have here is a transformer that has a turns ratio of about 50 to 1. And so we run about 5 amperes of current through the large number of windings, and on the small number of windings we get out about 250 amperes worth of current. And if you've always had a vendetta against nails because of perhaps a bad hammering experience, this is your demonstration. As we turn the transformer on, you should be able to see the nail begin to glow, as it is now, and the glow gets orange and starts getting a bit redder and yellowish here, and begins to get even maybe a little bit whiter, and the nail gets hotter and hotter, and as it heats up even more, you can actually see little bits of nail come up sputtering away, and finally it melts in two. If you want to be friendly and repair your nail, you can arc weld it back together like that, but that's optional. Anyway, one of the things that we sort of go around and round about the some of the so-called black body spectrum demonstrations has to do with the fact that most sources that we have, like an incandescent light bulb, the peak wavelength that you find in Bean's law is actually in the infrared. In fact, for an ordinary light bulb, it's around 1,000 nanometers or so, and you can't see much past 600 nanometers or so toward the infrared. Consequently, if you do something like the classic version of this, where you put a light bulb on a variac and look at a bare filament and just turn the variac down, you do see what is an apparent change in color, but it isn't so much because you're seeing the shift in the peak of the spectrum. It's because you're seeing the wings of the spectrum, and all the light is gradually becoming less intense. And because your eye is more sensitive to some parts of the spectrum than the other, you see that apparent color shift. If you actually want to do this with a light bulb filament, the best thing to do is use a thermal pile and a spectrometer so you can actually see the different changing shape of the spectrum from the filament. This is a nice thing to do because it's dramatic, and students, like Kevin says, just love to see the poor little nail bite the dust for science's sake.
Well, we're looking for a camera in the second grade.
Well, we were going to do that. You want to do that now, or you want to?
Could probably still look at it. It's all right, just leave it.
Could I ask,
It'll
do you
still be-
have a,
It'll still be hot.
do you have a ground fault interrupt on that circuit?
No, I don't.
Okay.
It would be a good idea, but this building is old, and all we have are circuit breakers.
I wish I could get rid of mine.
So you can still see it's much hotter than the back, the holder that we have on it here, so.
Want me to turn it on?
You probably have to make me shift temperature scale now. So right now it says my nail is at 231 degrees Fahrenheit. The portion that I'm looking at anyway. And so, getting much, much hotter right now. So it's greater than the maximum range on this thing right now. Whee! Okay, so that takes care of Wien's law. If you want to do the poor boys one like we do at Iowa, we just take a big metal ball and we go down to the shop, get the acetylene torch, and we heat that sucker up to red hot in class. And then when it cools down enough, you can't see the red anymore. Light matches off of it yet. So there's a lot of different ways. The light bulb works well for a lot of people, but it gets you some way to get into Wien's law and black body radiation. All right, our next thing that we have is, I think, like I said, we've already done the grading with the prism and grating, so we're moving on to the student line sources, and that's where you come in with the glasses that I gave you, because we have several different systems that we're going to look at here, and get into a little bit of spectrometry. But essentially, the first thing that we're trying to do in astronomy is teach people that if you have an element that is glowing, you should be able to tell what the element is because it has a unique fingerprint, okay? So hydrogen has a unique fingerprint that is different from helium. Helium has a different one from neon. Neon has a different one from mercury. And basically, if you throw those all together and use a computer, or if you painstakingly go through by hand, you should be able to separate out each spectrum and basically tell what a star is made of by looking at it with a pair of glasses or a more sophisticated spectrometer. But the glasses will work for our sources here. So, you need left yet, Cliff? Are you good?
I'm trying to get my cable connected here and it's fighting me. There we go.
I won't worry about you then. Okay, so if we look at put your glasses on, well, take your glasses off first, and look at this tube, which is hydrogen, okay? If you look at that now, you'll see that it's kind of purple and maybe a little pink, but if you put your glasses now on, you should see three distinct lines. You should see a very strong pink line, a blue-green line, and a purple line, and if you're really able to see into the UV a little bit more, there's another line beyond that. But usually people only see three lines for the hydrogen, okay? You want to hit the and Cliff has it on here on a spectrometer, so this spectrometer shows that on the TV.
Yeah, let me turn on the rear light so because that'll illuminate the, well, I guess
There you go.
you can see in this little spectrometer is actually a scale. The lower scale reads in nanometers. So that red line, the H-alpha line, the first Balmer series line, is a little redword of 650 angstroms, 650 nanometers, and the blue line, the H-beta, is a little blue word of 500 nanometers. Now, astronomers, this is one of the things that causes difficulty between astronomers and physicists. And I just made it because when I started thinking like an astronomer, I said angstroms, but if I think like a physicist, I say nanometers. If you really want to confuse people even more, the top scale above reads in electron volts. So for instance, that H-alpha line is has a little less energy than 1.9 electron volts per photon.
And
So now, the other thing, while we're at it, if you don't want to spend the 10 or 14 bucks for this spectrometer here, one of your other giveaway toys for the day is sitting right here. It's in 3 parts. You have the part that snaps out that has this. You have the grading that goes with it, and you have the directions on how to put it together. But this is also a calibrated spectroscope. So this can be used to tell the wavelength of a line just like this one here when you get it built properly, okay? And if you look at the back of your notebook, on the back leaf of your page there, I have tape to that, where these came from. Basically, the spectrometers are free. You might have to wait a while to get them because they only send them out like every 3 or 6 months or something. So you'll just put your order in and sometime later it will show up. But the only thing you have to pay for 45 of them is the $7 shipping to get them to you. 45, they come in bundles of 45 and they're free. So you can get calibrated spectroscopes that you can use in class or give away to your students for practically nothing. Which brings up the fact that I have some of that spectrum grading here that we're using for like on the overhead and stuff. If you guys want a hunk of that, just roll some out and cut it off and take it home with you.
I think Kevin has some of the star spectrometers that people can have too.
Okay. Okay, so we're going to turn off the lights again.
These spectrometers in Stanford are, they include the grading?
They include the grading, right. So you get everything for $7 for 45. So, okay. So now with your glasses off, you should see what we have here is, looks like the middle tube is helium, the pink one. The bottom one is neon. The top one is mercury, which is basically the lamps in an auditorium like this. Doesn't usually show it, but if you go to the gym, usually they have lamps that are more like this. So basically, what you should see now is one on top of the other. You should see 3 different fingerprints on the left and right side of your glasses there, and up in the corners, but we ignore those, okay? Now, if you don't like setting them up like this where people can come and grab a hold of the 5,000 volts, you can use ones like this where I have them set up like this where I can turn them on and off individually, or all 4 of them on together, and they're close enough together when they're side by side that I can do, you know, a star thing where the whole spectrum gets mixed up, but you can still tell where parts of the fingerprint are. Okay? So there's a lot of different ways to do that. Or if you just have a single power supply and then you plug the tubes in individually, a lot of people do that. Okay, any questions on line gratings? Oh, I forgot. See, Cliff, you didn't remind me.
Oh, yeah, that's the spectrometer out. Sorry.
What I have is, I need this one, right? If you have the money for it, you would buy a spectrometer from Ocean Optics. And hopefully,
Vernier is selling them too.
Vernier sells it, so does Sergeant Welch, Senko, all those guys. Pasco has them. If you have the money for it, I bought this one for apparently about half price when they first came out as promotional things. And I think if you beg hard enough, you can probably get it down to that price again. But what this is just a Ocean Optics spectrometer. This one is 350 to 1,000 nanometer wavelength, which you can see on the bottom scale there. What we have here is intensity. The nice thing about this one is that if I'm looking at a light source here, I can not only see where the wavelengths or the peak wavelengths are, but I can tell what the intensities are at the same time. So you can see down around 430, 40 nanometers, there's one that only has a 1,500 count peak, whereas the one around 630 is up around 3,500 or something like that. So very nice, and you can look at the spectrum tubes over there with this. Look at sunlight, look at the visible spectrum, any kind of thing. But I find that a lot of times physics people, if you go talk to your biology people or your chemistry people, they already might have that. Because that's one of the things that has been real popular in the last few years for those disciplines, and you can steal and use their equipment for that. Okay? But it's just another way to do spectrometry, but the nice thing about that is the intensity count, because you don't have to figure out what the intensity of one line versus another is. It comes out directly when you're using this type of thing. Okay? All right, we'll go back to
We set up a mercury vapor, little 12 or 14-inch bulb next to the spectrum tube. Turn it off and on, and you can see the mercury vapor inside of the fluorescent tube.
right. And
Very effective.
very effective. There's other ways to do it, and in fact, some of the old mercury tubes used to have sodium in it, or was it the sodium tube that had mercury? But so you'd see the sodium spectrum, and then it'd disappear, and then you'd see the mercury spectrum. Some of the old mercury street lamp stuff. So there's a lot of different things out there that can be used, but a lot of neat spectrometry. But even with the glasses, you can just send them downtown and say, how many different spectrums do you see walking around downtown? And some of them will come back with 8 or 10. The nice thing about the building spectrometers that from Stanford over here is that they have like 10 different spectrums already imprinted on the spectrometer that they can try to match.
And the gratings are single axis, not.
Gratings are single axis, 1,000 lines per millimeter, right? Whereas these are not.
You don't get the confusion.
Right, you don't get that. These are just for like looking at fireworks, but they're cheap. They're like 22 cents a piece. So I can throw them out to people and not worry about big expense. So, okay, band absorption. If you have the system like I have, where it's just the big grating here and a slit mask that you can put on your overhead, basically you can do the spectrum here. Oops, going the wrong way. But there's a lot of ways to do band absorption once you get this far. If you can put up a rainbow spectrum somewhere, you can do band absorption. The simplest thing would be probably food coloring. So if I put, let's start with blue. If I put blue food coloring on here, what you can see is that now all of a sudden it's absorbed all the red and yellow out of the spectrum. Okay? It's a big broad band that we're talking when we're doing food coloring. Green takes out all the red and yellow and pretty much all the blue and purple. Okay? And then red obviously will take out pretty much the blue end of the spectrum. So you can show band absorption that way, but if you want to get a little bit more unique, you can go buy some Vanish toilet bowl cleaner, the one that has the blue dye in it, and that'll work in much the same way as the food coloring. Or you can get, if you have a glass blower handy, you can get something called didymium glass, and it has several different bands. They're more closer to atomic absorption spectrum because they're thinner, but you can see several different bands there. If even that is expensive though, that's still pretty good expense. What you really want to do is go to the hardware store and buy something called a reveal bulb. It's got kind of a bluish tint to it. The bluish tint is because they have impregnated the glass envelope with neodymium. And when you lay that on the projected spectrum, this is what you see, which is there should be an absorption band here, and then there's a slight one over here in the greenish blue part. Okay. So, but this is a single element absorption, which is something that the food coloring and other stuff are molecular absorption. So you're going to have better banding properties from the neodymium bulb. Okay. Now Cliff has another neodymium one set up over here on his spectrometer. Right now he has a regular bulb which just gave us a rainbow spectrum. But as he puts in the reveal bulb now, and the reveal bulb comes in different sizes and different envelope packages. So he has it in the long tube, and you can still see the two bands that we showed over here with the other one that I had over here. Okay, so you can either light the light bulb like that, or you can just have the light bulb pass through from the overhead through the envelope, either way. So there's a lot of different ways for band or molecular absorption. Obviously, if you're looking at atomic absorption, you probably want to do the sodium flame and pass some white light through that and see at least a sodium single line, or if you have a good enough spectrometer, you can resolve the doublet, but most people don't do that. I just show a band of the two lines coming out. Okay?
You can use this pinky glow doodle.
Yes, the glow doodler works. If you go to Kmart or Walmart, there's something that is like a little transparent write-on pad. You can write on it, and then you flip it up, and it erases itself, and then you can write again. It's called the glow doodler. It's a little pink thing. But if you lay that on the overhead, that will do just like the didymium glass and give you a absorption spectrum also.
Well, the nice thing on that is, I mean, you can cut it up into little pieces and give it to the kids.
Right. And give it away, you bet. So, and they're like cheap. They're like $7 for the kit, you know, to make that thing. So you get a pretty big package of stuff there. Okay? Anything I have forgotten here? All right. Then we are on to sunspots. So a lot of people have trouble explaining sunspots to students in a way that they understand. So usually what we do is something like this. We have a bulb here, and if I turn things on and get enough stuff off the overhead, you'll probably have to shut that door quick. So here is my bulb on the overhead. I'm just using the optics of the overhead to show the filament of the bulb. Okay. The reason we want to do this on the overhead, though, is because once I turn on the overhead, that filament now turns into a dark spot. Okay, you can see the filament, but it doesn't appear to be glowing here because the overhead light is much hotter than the bulb that I had on in the first place. And that's basically what sunspots are, right? Just cooler regions of the sun, but still very hot. So you still have the bulb here glowing, but you can't see that because of the surrounding brightness of the other gas coming off the overhead. So that's one way to do it, and it's fairly simple and straightforward process of talking about temperature differences and the glow that blots out other things that you're trying to look at. Convection cells. We have that going over here, Cliff.
Yeah.
If you would, let me get a light on.
Cameras here.
Hopefully we can finish up in 2 minutes, right?
Ah!
So for convection cells, there's a lot of different ways to do this. You know, you can just buy yourself a lava lamp, right? That's convection cells. You can buy the lamps that have the confetti and stuff in them just to see how the convection works. Most of them will have a thing that goes around like this when they start going. A little bit more unique one is to have something like this, where we have some aluminum powder inside some Rico copier oil here. You just want something that's thin and clear as far as the oil goes. But basically, if you were close enough, or if we got the camera close enough, you could see that the convection on each one of these cells is going in a circular pattern like this. But the nice thing is I can mess these up, and within a short period of time, they will reestablish themselves into convection cells that were a different orientation than what we had before. You can see that starting to happen up here already. So it's a little nicer way to do it. All we do is gently warm the oil. It doesn't have to be hot at all, so you don't have to worry about the fire hazard or anything like that. You just warm it gently and it starts convecting right away. But basically this is very much like what the specular pattern of the sun looks like if you were to look at that in a filter and get it down so that you could actually see the surface under the corona. Okay?
The copier oil, that just cooking oil or what?
Like I said, pretty much any oil will work that the aluminum powder goes into. in that pint. So you have another half pound that you can give away to other people. So it works out pretty well.
And you can see where the little individual particles are coming up and going back down, and it looks very much like the pictures you see of the broiling sun.
Okay, so now we're into random walk. There are a lot of ways to do that. On your in your notes, you have a couple of websites where you can get like screensavers that do random walk. So you can just have the computer doing it, and they'll show a little random walk pattern. If you want to get more creative, you use a couple of bumble balls. If I can find out where to turn them all on. And you can put them in an enclosed container, or you can just let them walk around the floor. But if you have them in a kind of a little enclosed container, you'll find that they'll come together, knock each other around, and walk around a little bit. But you'll see that it takes quite a time before any of them travel any significant distance. I mean, they're going all over the place, all right? So, one way to do random walk, besides having to do computer stuff. Another way is if you are into woodworking and electronics, or if you want to do a special project, or have a student do a special project, you can make something like this one over here. All this is, all this is a shaker table with some pegs in it. The way we usually run this thing is to show a couple of different type balls, but this one is set up so that golf balls work really, really well. Basically, it's like a big pinball machine, okay? Okay? Sometimes they'll get out real fast, sometimes it takes them up to a minute to get out, because they'll go out and then they'll come back in again. Right? There it comes back in again. If you want to, you can have some balls that have exclusion points so they can't get through very easily. Okay? So that one takes a long time, a much longer time to get out than the golf balls. And if you want to make it even harder, use a smaller one. Because that one will take a significant amount of time traveling before it gets hit by anything. It doesn't get hit as often as the other one. So, a lot of different ways you can do random walk, but you know, it depends on how involved you want to get and how you want to play. Okay?
Are those pins random?
Are those pins? They mostly are, yeah. The outer radius was done by the guy had a compass and did a circle, and then he started just doing random circles off of that, and then at the intersection points he put the pins. But yeah, if you look, there's nothing unrandom about that. Yeah, there's no system there.
Yeah, the astronomy books often talk about the diffusion time of a photon coming from the center of the star. I've never figured out exactly why they allege that it's the same photon, but that's the way they talk about it. So, because of course, each time it gets scattered and absorbed, you ordinarily would think of it as something new, but that's what they say anyway.
Yeah. Okay, in your book you have how the fusion model is made here. It's just basically 3 magnets and a piece of iron that looks or is the same size as the other magnet. So what happens is if you have them so the magnet poles are facing each other, you get like electron repulsion where you can slam these together and they're not going to stick, okay? But now if you turn it around so that the iron piece is facing one of the other magnets, what happens is that as long as the iron piece is close enough to, or is farther enough away from this magnet, it has the same domain orientation as the other magnet. It looks just like a magnet, so you get repulsion. But if you want to do the strong nuclear force, what you do is if you slam these things together hard enough, they stick. Because what happens is half the domains now have switched to the other magnet, and so you get a sticking effect there, which is strong nuclear force, right? Distance versus sticking or repulsion. So So anyway, this is my nuclear fusion model. It's fairly easy to do. You can use PVC pipe and just epoxy your magnets in according to the diagram that's on there. And like I said, you've got electron or fusion going on here that you can play with. But you can also, see how far you've got to get before they stick together. It's a fairly nice model for just, it's about the only model I know of that can accurately mimic the strong nuclear force. Sunsets. You want to do that, Cliff, or do we? Kevin, how much time do we have? What's that? You just want to cut it off? Yeah, okay. All right. So for sunsets, usually what we're going to talk about is, we call it sunsets, but actually what we're doing is talking about scattering that takes place in the atmosphere. So what we do is usually use some kind of, some jar of water. We put it on the overhead projector and look at the light coming through it from the overhead onto the screen. Now what we are going to do is Cliff is going to put some pine sol in there. And you can see that right now the light is fairly white, but as he adds pine sol to this thing, now you can see it's starting to get more of a yellow haze. And as the pine sol droplets break up inside there, there will be more scattering. So this will go from yellow to orange to reddish orange, real red. And eventually, if you put enough scattering particles in there, it will go to extinction. The other part of this is that if you are able to see down here, sorry, you good?
Triple or something? Yeah, I'm okay.
If you are able to see down here, if we're more red up here, it means that more blue light is being scattered off of this container out here. So you should be able to see a polarization effect here if I have a polarizer here that I can run back and forth, okay? And for you guys over here, you just need more stuff.
Want more?
Yeah, more stuff. Oh yeah, you can see it. It goes from a white to a blue. It's not very prevalent right now, but as we get more stuff into it where this is more orange, you'll be able to shut this on and off.
If you do this, this actually takes place over time. What happens is the pine sol forms a colloidal suspension, and you can speed things up a little bit by adding some more if you like. But if you wait long enough, it'll get positively orange looking on the screen and very bluish and polarized on the side. And if you keep going, it'll eventually become opaque, and you can scarcely see anything at all coming out, and very white and milky at the bottom.
And milk works real well too.
Now, pine sol, if you don't like to wait, just go get yourself some non-dairy creamer and just keep adding that in intervals, and that goes real fast then. And then you can take it all the way to extinction, where the light up there goes clear out, and all you have is scattering down here. Okay? Okay. Let's skip the me thing, okay? All right. So I think we're getting down to the end here. Conduction. We're talking conduction rods. Most of you are familiar with conduction, convection, radiation. And I'm going to turn this one on over here. Okay. All the way up? I do. Yep. Okay, so go ahead with conduction. Convection, radiation, convection. So convection we kind of already did already. That was the whole point of this lamp here. You can also do convection. Besides convecting cells, you can do convection itself. So for conduction, what we have is a series of nails that have been waxed to this copper rod. And as the conducting, the rod conducts heat along its length there, the nails should fall off in succession here. So you can actually see what part of the rod is getting hot over time. Okay. The other one we have going over here is radiation. And in this one, we have a big heating element over here. With a match at the focal point of this other reflector over here. If we have good radiation today, we should be able to light the match over here using that radiation that's focused from over there, okay? That will probably take a couple minutes, and you should see it smoke a little bit before we start. Okay, so over here we've already lost one nail, and we're working on the second. And so while we're waiting for those to happen,
Maybe I should, we have a guy here, Professor Umstetter, who is building a terawatt laser. It puts out a terawatt, but only for a fraction of a second at a time, 50 femtoseconds or so. Anyway, he did this demonstration in one of his classes, and I kidded him that this is, he calls this laser Diocles. I call this Diocles Light, and it's rated at 10 to the minus 9 terawatts. And I don't know if you can see up close here, but the match here is beginning to smoke, and I have every expectation that within a half a minute or so it should burst into glorious flame. We'll see here.
What is the rod?
That rod is copper.
Is it copper too?
Yeah. No, it's solid copper.
solid copper, yeah.
And the second nail is about to go there.
A copper tube would work just as well. You don't have to worry about that. Okay, so while we're waiting for these two, the next thing in your book is the Hoberman sphere. Basically, this is how we show conservation of angular momentum. We're talking star collapse, because you know, the two-dimensional with the figure skater thing doesn't work so well for students to wrap their head around. So this one, if you get the regular Hoberman sphere mobile attachment, and I have places in there that you can buy some of this, but you put a ball bearing fishing swivel at the top so you can rotate it like this. And then when you pull, you get conservation of angular momentum in 3 dimensions. So, and also if you do it fast enough, you should be able to see some centrifugal flattening. Okay? Because it'll resist your ability to pull it together, and you get centrifugal flattening at the same time. Works really, really well. It's only a few bucks, and it's much nicer for conservation of angular momentum. Okay? Are we there yet, Cliff?
Well, he spoke it. We should go.
All right, so
Watch the match, huh?
what is the next thing in the book? I think it should be membrane. So the membrane, all we're trying to do is show the gravity well, okay? If we have a gravity well like so, we can add our black hole to the center. It will show our curved space deformation here. So we can show some models of that, but also you can start doing things like you know, black hole versus a other star or matter flowing into the accretion disk, that type of stuff. So you can also use this as a sun and cometary orbit thing, because you'll see the precession of the comet as it comes around. So works out fairly well. You'll get a precessing thing here. Another way to just another way to show black holes and orbits. Okay, so we've lost our second nail over here. We're working on the third. We're still working on our match. Is that the deal?
Wouldn't it be easier just?
Not straight match.
We did succeed earlier. So, and also, so when we're talking gravitational collapse of stars, black holes, or stuff, obviously you want to talk about supernova. You can buy the little toy. It works sometimes, sometimes not so good. My problem with this is that the little ball moves too fast and a lot of people can't watch it, plus it bounces all over the place. So you guys with glasses on, watch yourself. So here goes. Oops, there it is over there. Went towards the cliff. Anyway, the whole idea is the fact that when a star is collapsing, all the molecules are collapsing under gravitation until they get down so far where one is starting to bounce off the other, and you start getting momentum that blows off half of the mass as ejected out into the universe.
Question. What happens to your demo if you leave that small red sphere off and just use the other three?
It just sticks open. This one, the other three balls can't come out.
Gotcha.
So basically what happens is usually this one sticks up like this because it's mashed up onto the other one. Tennis ball and basketball work well for this also, okay? But if you want to go higher tech, you will go something like this, where you buy some pieces of sheet plastic from a master car, and you cut them out into circles and then put them in a rail like this. You drop them, and you get the momentum transfer from the bottom to the top to the between all the other ones there. Works out pretty well. Okay.
This
one is slow enough that you can see it as it gets ejected out. So.
And you can do this with just one or two, depending upon what you want to show.
So you can take this down. You don't have to do a lot. Some people put up to 7 different little masses in there. I deal with 4 is all I can handle. So. Okay, so expanding universe again. The Hoberman sphere. You can buy these so that they have. You have blacklight sensitive vertices on these, okay? So I can do this in the dark, put a black light out here, and all you'll be able to see is the vertices going out, expanding like that. And that's really what we're trying to show is that, you know, every one is going away from all the others, okay? So just a Hoberman sphere with the blacklight sensitive, I can't remember what they call it, starry night or something like that, as far as the Hoberman sphere goes. But you look on Hoberman spheres and they'll have like 8 or 9 different types that you can buy. So it's not that large of a problem. The other one that we have is if you're, you know, I ruined Twit's demo on that, sorry. The other one is in 2 dimensions. Obviously, you can do this one where you can have a collapsing universe or a steady state or expanding like this. So you can do this with rubber tube. If you wanted to do Tygon tube, you can put balls on it and just stretch it, do that kind of thing. As we're waiting for radiation to take place, it may wait forever. You know, the simple way to do it is go buy one of those $9 1 meg spotlights and a radiometer, and then you can stand from across the room and make this thing work. And you know, obviously it's not light pressure, it's all heat. I hope all of you know that already, that is making this thing turn. So basically all we're doing is using the big spotlight as an infrared source here. Okay? So a couple of unique ideas there. If you wanted to do the same thing that I did here, only in a little different way, Cliff, I need my help here. Sure. And that is if you're talking about the states of the universe. Is it contracting? Is it steady state? Is it expanding? If you had it like this so that you have a wavelength, you know, if the universe is contracting, the wavelengths are going to be blue shifting, right? So they're getting shorter. If it's steady state, everything looks the same and there's no blue shift or red shift. But if it's red shifting, you know, the wavelengths are getting longer, so they expand out farther, right? So that's basically the whole reason that we have discovered, because everything that we see is red shifting, right? Well, everything we see is red shifting. And it's going much faster than they thought before, so they're thinking the universe is not closed like it was before. So there's a lot of theory that goes on that you guys can talk about, new things coming in all the time about the state of the universe. Non-Euclidean geometry, Basically what you're trying to get across is the idea that a straight line is not always the quickest way to something. We have the classic saddle shape. You know, if any of you don't have a potter that can do this for you, what you can do is take an inner tube, any inner tube. I use a truck tire, and I just cut out the inner radius part, and then you have a saddle shape. Okay. But the whole point is the fact that if I was to take a string with a certain radius, if I put it on a flat surface and then laid a string around here and cut my string, I'd have a string that was just so long. Well, if I do the same thing on the saddle shape, my string is even longer than on a flat shape like this. If I do it on a globe like this, where I have it and I draw my circle here, it's much shorter than the flat surface. So you end up having the same radius, but depends on what kind of curve you're at as to how long the string is. And that kind of comes into play a little bit when you're talking space geometry and things like that. I think we're almost down to the last one. It should be Geiger counters. Yep. We might have a bust the way it looks on this other one unless I line it up right?
Yeah, probably blame it on me. Okay, this is a Geiger counter, and you can hear it chirping away. It's chirping away because all the time cosmic rays are going through it. There's also radiation from the building, even from my own body. This festive orange plate is Fiesta ware, and if I bring my Geiger counter up to it, you can hear the Geiger counter go crazy. The reason that the plate is radioactive is the glaze that was used to make it has uranium-238 in it, mainly uranium-238, and because of that, it gives off alpha particles, gamma particles, and beta particles, a whole mishmash of stuff. If you want to make the point about the alpha particles, and you can afford it, one thing that's nice to do is to take this kind of gadget, which is I call it my alpha paddle. It's an alpha particle detector, and what it does is it ignores the other sorts of radiation and only picks up the alpha particles. And you can hear that it doesn't do much, okay, unless you get real close to the plate. I got a little problem with my cable here, but if I get close to the plate,
Right, ground.
shit.
That doesn't say there's an error?
Perfect science.
Well, sorry about that. Anyway, the alpha particles don't go very far in here, and consequently, you have to get up real close to pick them up. The other particles, though, travel quite a distance. The other little radiation sample I have for you that you can get, and you don't even have to go to an antique store, you can just go to your supermarket, and that's this stuff here, which is salt substitute. And the reason that salt substitute is radioactive is because it uses a potassium instead of sodium. And because of that, I need to make sure my little beta window is open. The potassium, one of the isotopes of potassium, potassium-40, is radioactive. It gives off beta radiation. And if I get this thing real close to it, you can hear the chirp rate go up. And if I take it away, it goes back down to the normal background or so. So this is a nice way to start talking about why some elements are radioactive and some are not, and why it is that potassium we see today has a particular combination of potassium-40 and the other isotopes of potassium, why it is that uranium is radioactive, but ordinarily the sodium you find in the world is not, and in fact how the elements themselves came to be created. So.
Okay. Questions on that? I threw in the vacuum bazooka because it helps me to get students to think about what is the normal state of the universe. It's not what they're used to, right? This planetary atmosphere and the world they live in is entirely unique. There's like 400 worlds extraterrestrial or extrasolar worlds that we have discovered so far. None of them are like this planet yet. So we seem to be a rarity in the universe, all right? But they're used to operating here. So I use the vacuum cannon to ask them the question, what is the normal state of the universe? And of course the vacuum part should give you that hint, that it's not the mass of the stars or a lot of stars, it's that most of the universe is vacuum. And it kind of gets across the thing that, you know, they have to start thinking like astronomers, what's normal? And then you throw at them the fact that, you know, when they're looking at the universe, we have only seen 4% of it. So there's 96% of stuff out there that we don't know anything about yet. And you know, that gives them another jolt to the system. And so it just kind of drives home the point that you know, what they're used to is not normal. And for astronomers, that's something to get around a little bit. Okay? So thank you all for your patience and time. Kevin, thanks for the extra time. And like I said, pick up a